Our presenter today is Dr. Tiffany Williams. Tiffany is a research chemical engineer in the Materials Chemistry and Physics branch at the NASA Glenn Research Center. She joined the NASA workforce in 2010, where she has worked as a materials scientist developing next-generation aerospace composites, electrical insulation, textiles, and smart polymers. Her current research interests include developing lightweight, multifunctional materials and nature-inspired materials for space applications and more efficient aircraft. Following Tiffany's presentation, I will be giving a short presentation on how NASA licenses technology to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box in the lower right corner of your screen, and we will answer them during the Q&A session towards the end of today's talk. So at this point, I'm going to turn it over to you, Tiffany.
Thank you, Amy. Like Amy mentioned, I am Tiffany Williams. I am from the Materials Chemistry and Physics branch at NASA Glenn. And I will start off talking about the background for this work. So between 2014 and 2016, I, along with other researchers at Langley and Marshall, were involved with a project through NASA Space Technology Mission Directorate, where the goal was to develop high-strength carbon nanotube reinforced composites that either matched or exceeded the specific tensile strength of carbon fiber. At the time, the application was for composite overwrap pressure vessels, and we wanted to see if nanotubes could replace carbon fiber for a mass savings benefit. So we started off this project working with a variety of bulk nanomaterials, such as carbon nanotube sheets, tape, and yarn. And while our focus was not to necessarily develop or synthesize the nanomaterial, we played a very active role with looking into different types of post-processing techniques that could significantly enhance the tensile properties of the carbon nanotubes in order for us to achieve our mechanical property target. So we spent a significant amount of time chemically functionalizing the nanotubes in order to introduce crosslinks. We stretched the carbon nanotubes in order to improve alignment so we could see if we can improve the mechanical properties that way. And we also irradiated the nanotubes with electrons in order to form covalent crosslinks. And throughout all of those processes that we looked into, we were able to make significant improvements to the mechanical properties, but we still fell short of our target. So eventually our material property or material supplier ended up developing a very strong carbon nanotube yarn material which is the material that we stuck with for the duration of the project. And I'm showing that in this middle image here. And we actually saw this project from its infancy, from us being able to identify likely nanomaterial candidates that would make a good overwrap material, to performing coupon level fabrication and testing of the nanocomposite overwrap that we eventually developed. And then we went along, and then we went on to wrapping the tanks with the nanocomposite overwrap, and finally completing this project with the flight test and demonstration in 2016. So we believe that we had many accomplishments working on this project, the most obvious being involved in the process to do a flight test demonstration with the nanocomposite structure, but there were also materials development successes as well. Through this project, we developed a controlled and continuous process to infiltrate resin into the carbon nanotube yarns, making our own prepreg material. And we did this using lab equipment that was used for making prepreg from other fibers. We also filament wound the nanocomposite prepreg using a filament winder, an industrial scale filament winder. And so if you, any of you are familiar with working with nanomaterials, you do know that it is a big achievement to be able to fabricate nanocomposites without having to make significant modifications to your existing processing equipment. And we were also able to measure the tensile properties of our formulations through split D-ring mechanical testing. And in order to gather sufficient mechanical property information about or for our flight tests, we conducted an extensive amount of tests that were designated to understanding how these nanocomposites would behave as an overwrap material under various conditions. So we were able to get throughout all of those tests, we were able to get a really strong understanding of the material performance of these nanotubes going into the flight test. And although the nanomaterial or the nanocomposite overwrap was not as strong as the aerospace grade carbon fiber that we are accustomed to for this application, the properties of the nanotube yarn by itself were quite impressive. So there are many grades of carbon fiber, such as the high modulus carbon fiber or high tensile strength carbon fiber. But so we do know that the nanotube yarn that we worked with was competitive with some grades of carbon fiber. We noticed that the nanotube material was very easy to handle and that we did not observe any fraying, unlike how it is when working with other bundles of fibers. And because of its fibrous format, the nanotube yarn was compatible with basic polymer composites processing equipment. And the most impressive characteristic of the nanotube that I noticed was how strong how a single yarn filament was extremely difficult to cut and tear. It was almost like fishing line. So I felt that instead of trying to modify these nanotube yarns into in a way to make them as strong as aerospace grade carbon fiber, perhaps a better approach would be, is to look into seeing how we could use this material in a way that we could make improvements to polymer matrix composites. And that was how this whole thing began. So polymer matrix composites are replacing metals in more and more applications because of their high strength to weight ratio. But one issue with aerospace grade carbon fiber composites is their stiffness. And the high stiffness is due to carbon fibers and also the brittleness of the thermoset resins that are often used. And so to introduce more toughness to make it more suitable for the application, a common approach is to add thermoplastics or rubber toughening particles to the matrix. But one thing about introducing additives to the matrix is that they raise the resin viscosity, which is something that you always try to avoid when processing composites. And another thing is that some toughening additives may even affect the cure cycle or the glass transition temperature of the matrix, sometimes either delaying the cure or reducing the glass transition temperature. Nanoparticles such as silica and other particles have also been considered as a way to increase toughness of the resin, and this is actually a more recent approach to introducing toughness. But all of those methods that I just described involve adding something to the matrix in order to enhance toughness. So perhaps a better approach is to avoid adding something extra to the resin to give you the mechanical properties that you desire, since really the only role for the resin should be to distribute the load from the fibers and to perhaps protect the resins. So developing a toughened hybrid reinforcement may be ideal. But hybrid composites are not new. They are great to use because they offer unique and synergistic qualities from combining one or more than one material. This could lead to enhanced mechanical properties, and hybridizing the reinforcement may also be an effective approach to increasing damping and also providing non-mechanical property benefits, such as a better thermal conductivity, electrical conductivity, or tribological properties. But the term hybrid composite reinforcement can imply different things, so it's important to distinguish. The reinforcement, hybrids can exist at the ply level, where you can use a combination of fiber types for either woven or non-wovens or a triaxial braid. In this example, a bundle of filaments made from a single fiber type is arranged in either the plus or minus bias direction, and a bundle of filaments made of a different fiber type will be arranged in, say, the axial direction. So common examples of this type of hybrid are Kevlar and carbon fiber, or a glass carbon and Kevlar hybrid, or even glass woven and Kevlar. But there are also mats that are made of chopped fibers that are considered to be hybrids. More common examples in literature report hybridized chopped fiber mats that are made of either natural fibers but different natural fiber types, such as flax and sea sole, or flax and jute fibers. There are also hybrids that can be made of different synthetic and natural fibers, and also different types of synthetic fibers. Ply level hybrids are also used, and they are often considered to be well, basically, you can make a hybrid composite out of this type of material by alternating between thick and thin plies, but made from a single fiber type. Then there are fiber level hybrids, where nanoparticles are grown from the surfaces of carbon fiber. That's a more popular example. And I've also seen in literature glass fibers that were wrapped with continuous carbon nanotube yarns around those micron size individual glass fiber filaments. And then there are hybrids that may exist at the toe level. And a common example of this is a commercially available spread toe consisting of carbon fiber with polybenzoxazole. But other than that, the hybrid toe approach, for whatever reason, is fairly uncommon. But it is this type of hybrid material that I will be discussing for this presentation. So carbon nanotubes have been predicted through simulations to have superior mechanical properties, but these properties have not been realized experimentally. So that is one reason why nanomaterials have not been widely used for load-bearing structures. But instead of trying to use a fully nanocomposite material for a load-bearing application, there are some advantages to making a hybrid from a carbon fiber, more specifically carbon nanotube yarn combination. For one, the carbon nanotubes that we used were very tough and not very susceptible to damage. So the role of the carbon nanotube yarn in this hybrid would be the constituent to introduce toughness. Oh, sorry, let me go back. Next, there is very little to no material property database about hybrids or preforms or two-dimensional reinforcement made from those two materials. So with the carbon nanotube yarn being made from a fiber and not particles, this type of material could be easily used in common composites processing equipment without having to make significant modifications to your process. And this can be more likely as carbon nanotube yarn production volumes increase and production costs decrease. Triaxial braids are a type of reinforcement material that has the architecture that can enhance toughness compared to laminates. Triaxial braids are known to exhibit excellent damage tolerance, and they have use in aerospace, sporting goods, automotive, and some energy applications. NASA Glenn has done an extensive amount of work with investigating the impact behavior of braided structures as well as modeling to understand the failure modes of braided composites. And depending on the application, studies have shown that failure can occur in either the biased yarns, those yarns being highlighted in the gray area, and also or the failure can initiate in the axial yarns, and those are the yarns that's highlighted in red in the A and C columns in this image. In almost all of those cases, failure initiated by fiber splitting. On the right, I show a digital imaging correlation map from a previous study where the red areas in the field strain image are due to toe splitting, but other areas of the triaxial braid, as you can see, were fairly undamaged. So according to this image, it shows that damage such as toe splitting may only be more prone to occur in specific locations of the composite. And if that is the case, then perhaps it is in those specific areas where the more ductile fibers should be placed in order to help minimize the failure. So a benefit to hybridizing a braid is its versatility. A normal braid consists of axial yarns located in the 0-degree direction and bias yarns existing in the warp and weft direction. If you have an application where you anticipate failure initiating in the axial toes, then you can introduce the hybrid toe and only the axial toes while leaving your regular carbon fiber toes unaltered in the bias direction. If you anticipate failure initiating with only the biased toes, similar to what we noticed in the field strain image in the previous slide, then you can hybridize only the bias direction while maintaining the stiffness of the axial toes that are made of predominantly carbon fiber. And if you prefer toughness in all directions, then there's nothing that would really prevent you from hybridizing the toes in all directions. But the point is that hybridizing a triaxial braid is tailorable to your specific application. So to determine if there was any benefit to making a braid made of a hybrid toe of carbon nanotube yarns and carbon fiber, we first measured the tensile properties of the fiber toes according to ASTM standards. And we measured the mechanical properties of 5 specimens per sample. I believe the ASTM standard calls for like maybe 4 specimens per sample. But the ASTM standard also calls for infiltrating the toes with resin and then curing it prior to mechanical testing. But since we made a change to the toe construction, I thought that it would be a good idea to see if we could observe any influence of the carbon nanotube yarns on the mechanical property or on the mechanical behavior of the dry fibers. So fibers without resin was looked into as well. And an untoughened epoxy was used to infiltrate the toes, and failure of the toe was observed after tensile testing using optical microscopy. So a toe of only carbon fiber was used as the control material, and then we looked at several hybrid toe configurations, all having increasing volume concentrations of carbon nanotube yarns. So the toe test showed this really nice trend where the tenacity increased with increasing carbon nanotube yarn concentration up to an optimal value, followed by the tenacity decreasing. The toe tensile test, or through the toe tensile test that we conducted, we noticed an increase in the load capacity and also the shape of the curves, the load displacement curves, both all indicating that more energy absorption was observed in the hybrid toes. Unlike the carbon fiber control, the hybrids did not demonstrate brittle failure. But one thing that I do want to point out is that we often report the tensile data for samples containing nanotube yarns in tenacity, which is in newtons per tex. And so one of the reasons why we do this is because the carbon nanotube yarns do not have a perfectly cylindrical geometry. And the nanotube yarns are also porous, so it is not a straightforward process to calculate mechanical stress like you would normal conventional fibers. So to normalize, the properties of the tow, we use TEX, which is in grams per kilometer. So I just wanted to point that out. So from our work, the good thing is that we did not observe an immediate knockdown in the tensile properties after making the hybrid tow. And one reason why this is the case is I believe that it is related to the unique architecture of the carbon nanotube yarn compared to the carbon fiber. So when you make a composite made of carbon fiber or any other fiber like glass fiber or boron or aramid fiber, you are basically coating resin onto the filaments like what I'm showing in this micrograph. And so you are basically relying on chemical interactions between the resin and the surface properties of the fiber to provide you with ideal interfacial bonding. When using the carbon nanotube yarns, on the other hand, this material, like I mentioned, is porous and it does not have a smooth surface. And so resin can actually infiltrate between the fiber bundles, these empty spaces. And so what you end up getting is almost like a nanocomposite embedded in a composite if you're making a hybrid tow of this material. And so I believe that this is one of the reasons why we got the interesting response in this observed in this material. Basically, it's just you have significantly more interactions or significantly more interphases in the nanotube yarn compared to just micron-sized filaments of the carbon fiber and the resin. So since the mechanical properties were improved with the introduction of the carbon nanotube yarns, the optimal carbon nanotube yarn concentration was determined with the carbon fiber material that we used. And so we felt that it was safe to proceed with braiding. So first, I found a way to make a master batch of a continuous tow of the hybrid, and then those fibers were loaded onto mini cardboard spools like what I show here. And these are the spools that are used on the braider. Carbon fiber was also used as a control braid because it helped us to define the braiding parameters that we used, such as what is the right mandrel speed to use and what is the right braid speed to use. So after braiding, we followed up with optical microscopy to help us confirm the coverage and the braid angles. So when braiding, you can find the braid angle and coverage factors using the equations on this slide, where the braid angle takes into account the mandrel radius and the braid and mandrel speeds. The coverage factor is basically the amount of fiber coverage that you will get in your braid. So this equation takes into account the surface area of the braiding yarns and the surface area of the mandrel. And in the image on this bottom right, I intentionally show the change in coverage factors from a low coverage factor where you have these open spaces to a higher coverage factor at the bottom of this of the same micrograph, and where there's hardly any open spaces. But your application will determine the best braid angle and coverage factor that you should use. After braiding, the braiding parameters were established with the carbon fiber only control. I then loaded the braider with the hybrid tows, and we developed the hybrid tube that was shown in this image. During braiding, these bobbins actually rotate in like a figure-8 direction. So basically, these fibers are moving over and around one another as it is being braided onto the mandrel. So my initial concern, my biggest concern with the braiding process was that the braiding motion and the speeds that we used would cause the individual carbon nanotube yarns to snap off. But that wasn't the case at all. And actually, it turned out to be that it was very difficult to even cut this this material, this tube structure, from its shape where it's braided onto the mandrel into into a flat two-dimensional layer. And it even took a while before I was able to find something that would even cut the braid without it snagging the nanotube yarns and destroying the braid in its entirety. I ended up finding a way to use electronic cutter, a cutter that's used for cutting heavy-duty fabrics, but that was the only thing that I was able to find that would cut through these bundles of the carbon nanotube yarns. I do want to mention that through braiding and toe testing, we were able to demonstrate the tailorability of this material and its potential to offer an ideal balance between strength, stiffness, and toughness. And so this can allow the infiltration of low viscosity thermal sets, either without or at a reduced concentration of rubber particles or thermoplastics. The braid can also be used with the thermoplastic resin as well. And because these nanotubes because this braid is made of carbon nanotubes and carbon fibers, it can also be compatible with a UV curing process for both thermoset and thermoplastics, which is an advantage to this toughened hybrid braid compared to a toughened hybrid using aramid fibers. Because those aramid fibers are UV sensitive. And in fact, there are reports where carbon nanotubes have even been looked into as being used as a photostabilizer. In our hybrid material, both fiber constituents pretty much have the same chemical structure, so there should be very little concern over poor interfacial mismatch or interfacial compatibility with using two different fiber materials in the hybrid. And the mechanism of toughness in this fiber, or at least in the carbon nanotube yarn constituent, it is not contributed to viscoelastic properties of a polymer fiber or what you would see in a polymer. And this material is not a ceramic or metal. It really is in a category by itself. So potential applications for this material could include fan casings or ductings or stator vanes in aerospace application. The auto industry has been using carbon fiber braids as wheels, so perhaps this material could be useful considering that damage tolerance and the ability for the composite to conform to complex geometry, such as in a wheel design, that would be important. Prosthetics such as artificial limbs may be appropriate for this type of blade or for this type of material, and also turbines used in renewable energy applications, and also in the sporting goods sector, where you could consider using this type of material for a hockey stick or a bicycle. So preliminary findings with this hybrid braided composite were very promising, showing that the toe level hybridization for use in a triaxial braid, it is able to offer location-specific properties for your application. In my particular study, I only tried out one type of carbon fiber and a single type of resin. So the properties for this type of composite could vary considerably according to the fiber type that you use or the toe size of the carbon fiber that you use. So one should take that into account whenever you're trying to identify the appropriate carbon nanotube yarn concentration to use. The type of braided construction will also dictate how tough the mechanical properties will be. So in other words, which fiber direction will be made of the hybrid toes, and would it be only the biased toes, or will it be the axial or all over? And finally, ply layup configuration will influence the level of toughness. So do you want to add the same hybrid braid in all layers of your composite, or do you want to alternate? There are many options to look into, and because there are so many possibilities, perhaps using a modeling approach would be good to include in the composite design process. So future work includes doing a more thorough investigation into the mechanical properties of the braided composite, as well as understanding the failure modes of this braided composite and differentiating how it differs from that of a carbon fiber braided composite. So that is all that I have. This technology, I think, is available or this technology is available for licensing. And Amy, I'll let you take over.
Once again, we really appreciate you taking the time today to be with us. And thank you, and we'll be in touch soon. Take care.